The form of Artin-Schreier I want to say is any involution on the closure of the algebra on the algebraic closure of the rationals is a complex conjugation. That is, any involution. Well, in fact, any finite subgroup. Yes, better put. Any finite subgroup of the absolute Galois group of the rationals is a two-element group, and one of its elements is a complex conjugation. That is, it has a real fixed field, and it's, well, obviously an imaginary extension of that real fixed field, because the algebraic closure is imaginary, is not real.
How can you say that something is a real field that requires an infinite number of statements?
No. It's a single quantified statement.
But you don't know how many
which unfortunately I can't bound right now.
Oh, so you're saying you do get an explicit upper, you do get an explicit upper bound in the number of summons?
Actually, that will follow from the Lagrange four-square theorem. And you have to modify that for algebraic numbers. I believe it still comes to 4 if you don't require them to be algebraic integers. Yeah, actually, I can put a bound on the number of terms needed here. What I can't put a bound is the complexity of individual terms.
You're saying 4 summands is enough? 4 summands is enough?
I believe 4 is. If 4 isn't, 8 is. I forget. It's a part I haven't, because I can't do this part yet, I haven't worked on going much beyond it.
But that's because you're over the rationals, or is that just in general? I'm just trying to remember the equivalence of formally
over the rationals.
Oh, the rationals, okay.
Yeah, but it's in any algebraic number field. It's in any algebraic extension of the rationals. So the Artin-Schreier theorem here, we can't talk about subgroups of the absolute Galois group because we don't have the absolute Galois group. But we can say, we can define, we'd like to define, okay, what is a complex conjugation on an algebraic number field? Well, on the one hand, it's an involution with a real fixed field. Well, it's, okay, on a non-real algebraic number field, it's an involution with a real fixed field. And we don't have them on real algebraic number fields. Sadly, I haven't quite finished this part of it either. I was hoping to. I believe that's the same as an involution on a non-real algebraic number field. In fact, I hope I can say it's an involution on any number field, such that for every normal field extending this one, there's an involution that restricts to this.
Somehow the fact that this is all finite extensions of the rationals has to be important because there's all sorts of involutions in Galois theory, Galois theory of C, right? Including ones with totally non-standard fixed fields. So where is that actually being avoided here? I mean, that's why I'm asking about the finiteness of, I mean, how do I see the difference between...
The Galois groups are finite.
Yeah.
The automorphism groups are finite.
Right.
So you got no transcendentals.
Right. Okay, I guess because it speaks everything explicitly from the beginning is finite extension of the rationals. You're not just saying we're working with algebraically closed fields or characteristic zero, which could be anything.
Yeah. And again, and not algebraically closed. That's what we don't have. Proofs of Artin-Schreier talk about real closures. We don't have real closures. Over and over again, where we would like to talk about an algebraically closed field, we have to say, given a field in which the problem is posed, there's some sufficiently large finite extension. Because we've only got finite extensions. We don't have closures. And that's what you want to do is over and over again is find that some, and so take Q and extend it by square root of 2. This has an involution on it, switching the 2 square roots of 2, which should not be a complex conjugation. And indeed, this involution does not extend to any involution on this field. The extensions of this involution here are cyclic of order 4. They just restrict to order 2 on this part. And that's the paradigm for the Artin-Schreier theorem. I believe, but unfortunately I can't prove it yet, that in any algebraic number field, if you look at automorphisms of finite order that lift to automorphisms of that same order on every normal field extending this, I believe we'll be able to show those are only the involutions and only the involutions with real fixed field. And if I was a better field theorist, I would know that. I mean, if I could ask Zoe Kostadakis, she would probably be able to do it. I should just ask her. I should just remember this. So the point is, again, to be able to get all of this actually stated correctly, so you can go to Ribot's theorem. Ribot's theorem says any continuous odd representation of the absolute Galois group of the rationals has the following property. When I succeed at finishing this, I'll be able to state that first part over algebraic in pound arithmetic, or with luck in exponential function arithmetic. Now then it remains to prove Ribot's theorem. Ribot's theorem, it starts with representations. We're looking at representations of the absolute Galois group, but only continuous ones, so those all factor through some algebraic number field. And we're looking at representations on the finite field with some number p of elements, but the proof immediately goes to the p-adics. So there's another thing that would then have to be bounded and gotten rid of. Of course, when you're working with p-adics, the whole point of working with p-adics is that this summarizes arithmetic modulo p to the n for every power of n. And over again, the way it's actually done, you take some condition that you'd like to prove, you show it modulo p, you show that you can improve it to any higher power of p, and then you show that you only needed to improve it to such and so power. I mean, that's the way it actually works now before people were worried about bounding as a theoretical issue. So the hope is that that will all work out for theoretical bounding also. Over and over you say, you approximate these by arithmetic modulo p to some n, and you show that some coarse approximation is fine enough for your result. So that's what I've been working on. You don't see an immediate way to bound.
I've got an idea.
Good.
But the answer is no. I've got an idea what might get around the problem.
Okay, thank you.
Thank you. Questions, people?
I'm not quite sure whether you choose this label, but I know you as a categorist.
Yeah.
Right. Now, going back into the ancient history of category theory, there's phrases saying like jungle of formulae and so on, and some of the quotations of Ironberg about eliminating subscripts and so on. I'm wondering whether there's another strategy for this kind of thing of asking, looking generally speaking at what the nature of the algebraic number theory is. Now, the algebraic number theory is far too difficult for me. It's stupid to understand it, but I do know that it has a lot. That its history is intertwined with that of category theory, and presumably with the notion of arithmetic topos. So could you approach this by looking at the kind of categorical logic that you need to develop whatever the textbook theory is, and say, well, let's say for the sake of argument that it works currently in an elementary topos with natural numbers. Is that true, by the way?
Yeah, I think it will. Yes.
Right. Can we cut down that kind of categorical logic to some other kind of categorical logic? Now, the unfortunate thing there is that nobody has properly written up the notion of arithmetic universe, which might have been a candidate.
Yeah, but this is all inside first order arithmetic, and it's going to work pretty much the same anywhere you do it.
Yeah.
This is something I was happy to agree with Harvey about at a meeting a couple of years ago, that once I think he's probably right, even once you're inside the axiomatic subtheories of second order arithmetic, it's all going to work the same, no matter where you do it. But certainly this stuff, this is all computation. This is all computation with naturals, and it's not going to depend on those larger issues. Now, other aspects of getting the proof of Fermat's last theorem into first order, yeah, absolutely. You want to be able to say exactly what's meant by taking a derived function, or exactly what's meant by an injective resolution. But for the arithmetic, I think it's just
stuff about putting downs on quantifiers. The only thing I recall seeing accurate logic about that is was bounded in their logic. Which I don't know whether that's anything like powerful enough to do algebraic number theory. Presumably not.
But here, over and over again, say, for example, we are not interested in the general notion of an ideal. All the ideals that come up in this subject they come with finite bases. You don't need some Hilbert theorem to show they've got a finite basis. The way they arise, they come with a finite basis here.
Steve?
I'm not quite sure how much this was already present in Paul's question. I think some of it was, but I mean, something that's striking me when you were talking about, all the time you've got the coding, you've got bounds on the coding. Paul mentioned arithmetic universe. Now, one invented then in order to, go to Gödel's theorem and try and instead of dealing with coding into natural numbers all the time, deal with things actually as they naturally were. So, you've got a finite string, you've got a finite string, you've got various objects in the universe. So that's what I was wondering when you were giving the talk. Is there some way of sort of getting rid of the coding, which actually would make the whole thing more transparent? Except probably harder to work the details out. Because arithmetic universes. You said what did you want to do? The thing you specifically mentioned was strings, and that's the particular thing arithmetic universes add to all the finite limits and coding limits that you might want to agree on. So I'm not saying I know how. I don't even understand, in full what Ondrej did with Gödel's theorem and how he used that categorical structure to hide the coding. But I wonder if there's something similar that could be done here.
I wonder, but in a way, the coding is part of what I want here, and I don't care about a lot of the details of coding. But what I want to establish is that all these theorems were quite concrete, that you really did know where to look to set to do all the calculations. Yeah. And I think Hilbert's right to say that often that's a matter of setting a bound. I want to show concretely that you can actually do all these things. And so what I don't want is to, for example, I don't quite like even here just saying there's no sum of squares. I would like to be able to set an explicit bound on how far you have to look for this sum of squares. Again, the problem, not that these might be excessively large numbers. No, it's almost the opposite. They might have excessively large denominators. And so I think that here the whole point is to be very concrete. And that's a little bit at odds with the idea of an arithmetic category, although don't wait for me to say I wouldn't learn something from Joel.
I've never heard of, what is this arithmetic universe business, or how should I just Google arithmetic universe or Joyal?
Unfortunately not, no. So, do you know what a pre-topos is?
Probably. I can look that up on NLab.
Think
I know what a topos is.
Think of elementary set theory as taught to computer science students rather than math students. So in particular with finite power sets instead of general power sets.
Is that what we teach them?
Roughly speaking, yes. So a pre-topos is well, I could give you the categorical definition, but the most complicated bit is that it's got equations of equivalence relations. And an arithmetic universe, arithmetic universe adds to that three monoids or disks.
Right.
Or finite power sets.
Now, if I search for this as arithmetic universe, I will find.
Unfortunately, very little has ever been written up. And two of the people who've written about it are in this room.
Mini Maietti and part of it's written quite a number of papers, and she also did a joint one with me, which is on my website as well.
All right, I'll start, okay.
But I don't want to just say, you know, there are strings. I want to know how hard it was to calculate the string. But only in a fairly coarse sense. I'm not like I said, this is my problem when I read the computer science literature. They want to know for real how to calculate it, and I don't need all of that. But I do want to keep knowing it was calculable.
I suspect the answer to my question is negative, because things like Storm's theorem are what one might call absolute lemmas. Whatever your way of approaching a problem is, you're going to have to do something like Storm's theorem.
Yeah. Yeah, I was at a panel where Harvey and I were on this panel discussing categorical foundations. And Harvey, knowing that it was a little odd that he would be on such a panel, really wanted to rise to the occasion. And he said all the best things he could say about categorical foundations. And one of them was that by the time you're below second order arithmetic, it's just the same. And I think he was exactly right about that.
Any more questions? Very quick, perhaps. In the Sherlin-McIntyre Vandendries approach, we were talking about the rational field a lot. And you say, well, we can't quantify with natural numbers, we don't have the natural numbers. But you do, because we've got Julia Robinson interpretation of the naturals.
No, you can't quantify over degrees of polynomials in a family. That's right. Yeah, you can quantify over the naturals.
So is this issue about Julia Robinson, these Julia Robinson definitions of any use in that context? You said at some point that they would use
it comes into this.
There's Bjorn Kunin's improvement of that. I'm not sure how far that brings you, but you got some complexity down.
Yeah, I think not. The problem there is that a polynomial is a string, and we can't quantify over strings of different lengths. Because a string is, the way you quantify over cubic polynomials is you say, for every A0 and every A2 and every A3, there is. And you needed those 4 quantifiers. So you can't, that's where you can't do it.
I suspect the sum of squares, and there was a related question about Hilbert basis theorem, which came up in the conversation at one point, and that must be a similar issue.
Oh, the Hilbert basis theorem, the perspective I didn't mention was the reverse mathematics perspective. A fair amount is known about Galois theory and reverse mathematics, but always for countable fields. And countable fields can be horrible compared to the field of rationals. And what you keep finding is that nothing close to elementary function arithmetic is going to suffice for the Galois theory of countable fields. But I don't need the Galois theory of countable fields. The Hilbert basis theorem is not going to be is not going to be provable in anything close to this. But that's why I'm happy I don't need the Hilbert basis theorem, because my ideals they don't even arise as ideals, they arise as fucking strings.
So my suggestion is that you're looking at elementary function arithmetic, EFA. My suggestion is that you add to it some sort of sigma 1 collection axiom. Now the advantage is you've got some scheme which will give you other ways of getting bounds. And that's exactly what collection does. But when you've used that scheme and you've got a concrete answer, so we've got a lemma which goes via this collection axiom that relates to the number of squares that you need. When you've finally got your answer and it's in the right form, you can use some conservativity result to eliminate that collection axiom afterwards. And that seems to be a sensible suggestion to go.
Yeah, the suggestion from actually Steve Simpson, who he and I didn't used to make such friendly suggestions, was to look at the WKL theorem star.
And it's the same idea.
And it's the same,
It's exactly the same idea. You jump up one level,
yeah.
But when you finally got your concrete result that you want out of it, you use the fact that it was a conservative extension anyway to pull back down.
Yeah, and that's something so far, I'm not real used to partial conservative results, but I mean, I can learn it. Yeah, because this WKL0 star is not conservative over EFA, but it is.
That's right.
For
so
some number of quantifiers.
There's a first order version of that, which is also suggested.
Yeah.
That's the second. Any other questions, points? Well, thanks very much again, Colin. Well, we've got around 10 minutes for those that want to go to this other talk that's going on today. Down in lecture room A, I emailed everyone, or emailed Friday, it's down in lecture room A, and it was billed to start at 6:30, so in 10 minutes. In this building, on the ground floor, just next to the lobby, and we are going to be told that we've been told all the wrong history about Pythagoras. What's his second name? Piers from Cambridge. So that's in 10 minutes, and after that we'll go straight off to Staff House for a quick beer and decide how many people stand along the table.
Yeah, there are two reasons I make it. One I've only got one more slide to go. So
you don't go into the bus would normally turn into campus and
Oh, that round, then, yeah, you did.
Doing following round and then doing your
So it means that if this
But somehow, I mean,
Well, not quite that.
everything is, so if this is proven, I can understand. No, and then you can't have waterfall.
That's something I want to
Well, not in every day.
Exactly where
my business is probably today is a friend of mine from Mexico. She may be, I don't know where she's going to so like, she's going to come in with me, and I'll be in and then